First of all, thank you, Bastiaan and Prisma, for having us. I'm Arend van Beelen. I'm from Amsterdam. I work for what I think is a pretty cool company called Fiberplane. What we do is we create collaborative notebooks for DevOps and SREs. We are based in Amsterdam, but we also have people living here in Berlin, Denmark, the UK, and for a couple months more, also the US. But don't worry, we're not letting go of our US colleague. He's actually moving to Germany soon. Tonight, I will be talking about full-stack WASM development with fp-bindgen. What does that mean? Well, I hope this presentation will make that clear for you. But more specifically, I'm going to be digging into how we integrated Rust into our React Redux frontend as sort of a case study. And towards the end, I hope I will also do a little bit of live coding to show you how that works in our day-to-day. So first question, what is full-stack WASM? Well, I hope that most of you have already heard of WASM or WebAssembly. But for those that don't, WebAssembly is basically a technology for running compiled code such as Rust in your browser. Or at least that's how it started out. Because unlike JavaScript, which also runs in your browser, WASM actually runs in a completely isolated sandbox environment, which is really great because it means it cannot do anything. Like unlike JavaScript, which has access to the DOM, your window object, with your camera, geolocation, whatever. WASM cannot do anything unless you explicitly tell it what it has access to. And that's a really great environment from a security perspective. And so server-side people started thinking like, hey, this could be really useful for writing secure plugins. So they also created server-side runtimes. So that's basically what full-stack WASM is. It's like plugins or WASM modules that can run both in the browser and on the server. Now, not all WASM modules are automatically full-stack, right? Some of you might have heard of fp-bindgen. If you use that, you kind of expose most of your JavaScript environment from your browser to your WASM module, which is great if you want to give it the capabilities that your browser also has. But it's not great from the security perspective, and it's also not great from a portability perspective, because you're tied again to the APIs from your browser, and you cannot use that on the server. So in this talk, we're going to be focusing on WASM modules that run both in the browser and on the server. Now, why would you want this? I kind of already gave away the first use case, plugins that can run in both environments, right? And for us, Fiberplane Providers are one such use case. Like, providers are WASM plugins for connecting to arbitrary data sources. And a data source can be something that provides us with metrics or logs. And they can be accessible through a public URL that you can access from your browser. But in a lot of cases, those data sources are running inside of a private network of a customer, and we cannot access that. So in that case, a provider needs to run inside of a proxy server that is hosted by our customer itself. So that's one use case why we really wanted to have these full-stack plugins. The other case, which I'm going to be digging into a little bit more tonight, is FiberKit. FiberKit is what we call our core Rust logic that we run inside of the browser to power our own React Redux frontend. Now, what is fp-bindgen? fp-bindgen is a tool that we created that allows you to generate the bindings that you need in order to create Rust plugins that can run inside either a TypeScript runtime or a Rust runtime. And the bindings to let the plugin communicate with those runtimes are actually really complicated, because WASM by default only communicates in primitives, basically just integers and floating points. It's very limited, so that is very problematic also if you want to communicate your own custom data types. So if you want to communicate like arbitrary data types, what you need is you need to serialize those. You need to put them into a special memory region that the WASM plugin can access. You need to take the Rust allocator into account. And then you can hand a pointer to the plugin, and the plugin can do the deserialization again. It's a lot of hassle, and that's why we have fp-bindgen to take care of that for us. It abstracts all of that away. Now, how do you use it? Well, there's 4 easy steps. The first one is you create a protocol definition, and then you let fp-bindgen generate the runtimes and the plugin bindings. You integrate those runtimes in your own project, and then you can start writing plugins. I mean, easy peasy, right? It's actually really involved. So rather than trying to explain this in detail, sorry, I'm just going to show you. So that brings us to demo time. I have here prepared, I will zoom in a little bit. Oh, a little bit too much. A notebook. Like, this is how we do incident resolution with Fiberplane notebooks. You have some graphs. Today we're going to be very destructive with this notebook. I'm going to create a button called clear notebook, and it's going to wipe this notebook. That will be the demo. So how do we do that? Let's look at the presentation again. Oh, this one. What's step 1? We have to define a protocol. Well, I'm going to be using the FiberKit protocol, which is already there, but I'm going to extend it to implement the functionality for a clear notebook button. So we take our FiberKit protocol. I hope you can all read this. As you can see, a protocol is defined through 2 macros, an fp import. Can maybe even do it a little bit bigger for the people in the back. There's an fp import macro and an fp export macro. fp import defines all the functions that the plugin can import from the host environment. In this case, our TypeScript frontend. There's only a single function that it imports, which is for logging messages. That sounds a bit underwhelming, but it's actually pretty great because it means our Rust code, our core logic, is fully self-contained. It has no other dependencies on the TypeScript code. And in the fp export section, it exports functions that are implemented inside the plugin and which our TypeScript code can invoke. So the one we'll be focusing on today is the notebook reducer. For those unfamiliar with Redux, reducers are basically pure functions that take a state object and an action and reduce that to a new state. That's in a nutshell how state management with Redux works. So here is the actual implementation of this function. Just for clarity, this notebook reducer JS is like our JavaScript exposed bridge, which receives a notebook ID, which is a string. We use that notebook ID to get the look up the old state, and then we take this old state, put it in the actual Rust implemented notebook reducer, together with the action, and out comes a new state. That's like the deal. Now we take in this notebook action, this is how any action or event, or whatever you want to call it, how any action goes into the reducer. So we have to extend this notebook action to perform a new action, such as our clear notebook use case. I'm going in here. These are all the actions that we currently can expose from TypeScript to Rust, at least for this reducer. So we add a clear notebook variant here. We save the file, and that's for this use case, that's the only extension we need. So what was step 2? Well, we let fp-bindgen generate the runtimes and the plugin bindings. Again, this has been done before, so we are going to look at some existing bindings. Here is the notebook action, the TypeScript version that got generated by fp-bindgen, but it does not have a clear notebook action yet. So what I do is I go into our protocol directory. I will zoom in a bit. And I just do cargo run. Will take a couple of seconds, but this will yield us an updated protocol bindings. Should not take too long. Though we do have the recording software running, so it could take a little bit longer than I thought. And there we are, bindings generated. And what do you know? There is a clear notebook action as well. So what is the next step? We integrate the runtimes. Our frontend has integrated this FiberKit module, but usually at step 3 you need to think about, like, okay, you have to implement the functions inside of the runtime that the plugin can import, which in this case is just only the log function. But you also need to think of how to load the plugin and how to invoke the functions that are exported by the plugin. Most of that has already been done, but what we want to do here is we want to dispatch this clear notebook action, right? So let's just do that. I mean, we just take our React component and we're going to add a button. It'll be an ugly button, I don't really care about that. And what we do is dispatch, which is also provided by Redux, and type is clear notebook. There it is already. Clear notebook. Save. And if we look here, I might have to reload. And if all is well, we will see an ugly clear notebook button. There it is. I can click it, but obviously nothing happens yet because nothing has been implemented yet for the clear notebook action. So that brings us to the final step. You would write a plugin, and in this case it means I'm going to extend the plugin functionality by actually implementing a case that handles the clear notebook action. And we see here that Rust Analyzer has even already highlighted where we need to do that, because we have a missing match arm. Well, up. Oh, this happens sometimes. I'm just going to do it like this. Up. Okay, there it is. So, how do we implement this clear notebook action? We're just going to take our state and we'll say, okay, we'll reset the title to be the new, or to be the original default notebook title. And we take our list of cells and we're going to assign it an empty list of cells. Okay, I think this should do the trick. And I go to the console again. I'm going to hit enter here in the bottom one, which will trigger a new FiberKit build. I add the -- fast, which prevents some optimizations. It will still take at least a minute. And maybe a little bit more with the recording, but we'll be patient. One thing that might be interesting to discuss while this is compiling is, I said I was talking about plugins, right? But this FiberKit thing doesn't really feel like a plugin. It's basically our core logic. It's certainly not an optional plugin for our frontend. Our frontend really relies on this thing being there. The reason we used fp-bindgen anyway, despite the fact that fp-bindgen is kind of geared towards the usage of plugins, is on the one hand because, well, we needed fp-bindgen for the providers, right? And once we were working on that, we kind of felt like, okay, this is really cool. It's also pretty high performance because providers or fp-bindgen uses message pack for serialization, which is compared to WASM pack, which uses JSON. It's a nice nice thing there. But then we thought like, okay, if we can unify the tooling for both our providers and our FiberKit logic, then both will communicate with each other in message pack. So we can pass data from one to another without even decoding it on the TypeScript side. So it helps us with some performance optimizations there as well. Meanwhile, it's still building. Any minute now. Maybe I can already take questions. Yeah?
The reducer was only returning the new state, it was also returning a side effect. Sorry, could you talk in this little cube here? Actually, the reducer, it was not only returning a new state, it was also returning a side effect. Can you think of this as some kind of Redux middleware implemented by Rust? Or?
It is indeed a Redux middleware trick because, well, we have this core logic in Rust, right? But it does not depend on the TypeScript environment. And it also cannot and should not trigger side effects directly. But through a side effect descriptors, it can instruct the TypeScript side like, hey, I want these side effects to be triggered. So on the TypeScript side, there is a custom middleware implemented that takes the descriptors and triggers the actual side effects again. Cool. It's got built, and let's look. We have our demo notebook. It should have reloaded already while I was answering the question, so let me hit the button and see what happens. Bam. And that was the demo. I don't know if I have time for questions right now. Yeah? All right.
Someone has any question, please talk in the queue. Sorry.
Thanks for the talk. Very interesting. You said like you wanted to move the front end part, let me call it, right? Also to Rust to be able to talk to your back end parts, basically, right?
Yeah.
In a very simple form.
Yeah.
But aren't you like you then don't have to talk to the TypeScript and said that would bring you like optimizations, but aren't you then moving, at least you have to serialize and deserialize the state at some point, right? In your app. And
correct.
So is it more performant to do this and serializing the state and going back and forth there than going to TypeScript directly in a way?
It is, and the reason it works is I can show you a little bit about that. That is hidden inside of here. So this notebook reducer JS function, this is the bridge that we have. And the interesting part is that because it only takes a notebook ID as one of its arguments, we don't serialize state when we call this reducer from TypeScript. We only have to serialize this string and the action. And the state itself is kept entirely in the Rust side in a inside of this one. This is purely an optimization to avoid this serialization overhead. And then whenever the new state comes out, we compare the old state to the new state. And based on that, we generate a state update, which is a minimal diff of the between the states. And that is what we pass back to JavaScript. Does that answer the question?
Yes, I think so. But that one you do serialize in DC.
Yeah, you still need some serialization, but we try to do it as little as possible. Yeah.
Okay. Thanks.
My question would be what kind of logic do you execute in the Rust code that justifies this overhead?
That's a very good question. I kind of skipped over that indeed, but the main reason why we really need this is because we have quite some complex logic to deal with operational transform, which is the logic for handling conflict resolution in a multi-user environment. And this logic needs to run also, again, both on the server and on the client. Well, this is thousands and thousands of lines of code, and it seemed infeasible for us to write that code twice, once in Rust and once in TypeScript. So that's why we took the same code that we already use on the back end, and I thought like, okay, we should just run this same code in the front end as well. So that was not really done from the perspective of performance. It was really a pragmatic decision, like we cannot build this thing twice, because also the tiniest discrepancies between the two can lead to bugs. That's not something we wanted.
I think there was one more question. Thank you.
Okay, thank you for the talk. Very interesting. How does it compare to fp-bindgen? So I'm using fp-bindgen. It has some limitations, like the TypeScript definition files it creates are not great, and you can't like serialize a vector of more complex types. What are the main differences between fp-bindgen and fp-bindgen?
Well, you indeed are touching on one of the differences already. The way fp-bindgen generates type definitions for complex data structures is not something we really liked. You can still do it, and they will be serialized over JSON. But before we went towards creating fp-bindgen, we used a tool called TSRS, which can also generate TypeScript type definitions from Rust. And we hooked that up together with fp-bindgen to have the type safety that we needed. It worked. It was hard to integrate the two, and it required us to write some unsafe glue code, or at least not type safe glue code, not unsafe in Rust definition. So yeah, that was really a great experience. The other difference is indeed that fp-bindgen uses JSON serialization, whereas we use message pack. To be honest, message pack JSON within a pure browser environment, the performance difference is negligible, but for the server environment with a Rust plugin and a Rust host, there it speeds things up a bit. Other differences, well, fp-bindgen is really aimed towards exposing your browser APIs to your Rust code, whereas we are more aimed towards a plugin use case where you define a limited set of functions that you want to expose to your plugin, and those are the only functions that are accessible across the bridge.
Okay, thank you. Sounds great.
Welcome.